Let's look a little more closely at some system configuration details as well as the point of interconnection for our system. First off, the inverter equipment disconnects. We know that we're going to need an AC and a DC disconnect for the inverter, and depending on the specific inverter, there's different options and ways to approach that. They have to be within 10 feet of the inverter. Now, we'll get there in a minute, but we're going to be using an inverter combiner panel to bring the output of the 5 inverters together and then run a single circuit to the point of interconnection. So depending on the layout, we might be able to use the breaker in that combiner panel as an equipment disconnect. We might not. And with 5 inverters maybe mounted on a wall, that 5th inverter in the line down from the point of interconnection, or that AC combiner panel rather, probably going to be further than 10 feet away. So we're going to take the easier approach here. We're going to utilize the integrated DC disconnect that comes with the inverter. And we're also going to use an integrated inverter AC disconnect. Now, that may not be available on all inverters. DC disconnects are very common, or at least as an option. AC disconnects less common even as an option, but many inverters do have them. Of course, for either one of these, we could use an external switch, although with the integrated fused combiner on the DC side of the inverter, well, we're going to run all those source circuits in before we parallel them, so the built-in switch in the inverter works really well to shut all of those circuits off from the inverter itself. As I mentioned, combiner panel breakers could be our disconnect. Here, because of the spacing and the distance to the combiner panel, we'll use an integrated disconnect, or if you needed to, you could use an external switch. It could either be a rotary switch or a knife blade type switch on that AC output circuit. The label requirements, of course, we're going to have our maximum DC voltage labeled, 983 volts in this case. We'll put that on each inverter on the DC wiring cabinet where our PV source circuits come in. And then the PV system disconnect is also going to have to be labeled, and we'll look at where that label is going to go when we have a schematic of the system coming up here in just a little bit. Okay, let's size the output circuit overcurrent protection devices for our inverters. Remember, we've got 5 50 kW inverters. We get the inverter maximum AC output current from the manufacturer. In this case, it's 60 amps. That's right off of the data sheet. And the output breaker then is going to be sized on 125% of that value. So 60 amps times 1.25 gives us 75 amps. Now, we've got to recall 240.4, our standard, or maybe it's 240.6, you can look it up and check, our standard overcurrent protection device sizes. 75 amps is not one of them. It's our calculated minimum value. So what do? We go up to the next larger size, 80 amps. So we would have an 80 amp 3-pole breaker for line 1, line 2, and line 3 for our 3-phase inverters on each of the inverter output circuits. Okay, now that we know each inverter is going to be backfeeding an 80 amp breaker, we can size the inverter AC combiner panel. We'll follow the rules in NEC section 705.12b33, and we see that all we do is add up the handles of the breakers. We've got 80 amp breakers, there's 5 of them, 400 amps. Remember, we don't worry about the breaker supplying the subpanel, the main breaker, and in this case, we don't have any other load breakers, data acquisition system or anything like that. 80 amps times 5, 400 amps, that's our minimum bus bar rating. Pretty easy to do that calculation. So we'll have a 400 amp supply breaker to this panel as well. That's going to be at the point of interconnection. It may be fuses. It's going to be some kind of overcurrent protection device, probably a breaker if it's a load side connection, fuse disconnect if it's a supply side connection. But I do want you to remember, since we are fully utilizing the bus bar capacity in this subpanel, all 400 amps of it, we can't put any other breakers in here. Now, even if we weren't fully utilizing the capacity, we'd still have to put this label on here, right? So that saying that, hey, multiple sources of power, the sum of all the breakers can't exceed the bus bar rating. In this case, our 580 amp breakers gets us all the way there. Nothing else can go in this panel. If we needed to run circuits for other associated loads, then we would have to have a larger bus in the panel to accommodate that. Okay, so let's look at the point of interconnection. First off, can we connect on the load side? Often going to be a less expensive and easier to execute approach, but we know that load side connections are going to limit us in terms of the amount of current we can supply to the existing equipment. 705.12b31, the 100% rule, not an option. The main breaker and the bus bar ratings are the same. There's no headroom. We can't use that option for a load side connection. What about 705.12b32? That's our 120% rule, where we say Imax, the continuous output current of the inverter, or inverters in this case, times 120 times 1.25, plus the main breaker supplying that has to be less than or equal to 1.2, 120% of the bus bar rating. So we've got 5 inverters. Each one is 60 amps rated continuous output current times 1.25. 375 amps is the Imax for the combined AC output of the 5 inverters. The main service panel at this site is 1200 amps. It's got a 1200 amp breaker, 1200 amp bus bar. 375 from our inverters plus 1200 is 1575. Well, our bus bar, 120% of it, 1200 amp bus bar times 1.2 is only 1440, so we can't do it. The main breaker, 1200 amps, plus 125% of the continuous output current of the inverters is more than 120% of the bus bar rating. 1575 is greater than 1440. So load side connection, not any way to do it on this existing equipment. How about a supply side connection? That's going to be what we're going to look to do here because, well, the load side's not going to work. So 705.11 in the National Electrical Code addresses supply side connections. We have 5 inverters, 60 amps each, 300 amps. Again, to get our minimum overcurrent protection device size, we multiply that by 1.25, 375 amps. That's not a standard size. The next standard size is 400 amps. So we'll have a 400 amp overcurrent protection device protecting this circuit at the point of interconnection. Probably something like we see on the slide here. A fused disconnect, 400 amp fuses on each of the phases. The top of it is the power source. The bottom of it goes to the inverter panels, and that will be at the point of interconnection. How's it going to physically be done? Well, the actual point of interconnection, right? So where these wires go to, and they run to the actual point of interconnection itself. In this case, we've got a service where we can actually bolt on to existing lugs in the large distribution equipment. Now, you got to keep in mind that when you do that, there are some risks. We don't want to violate the listing of equipment. You can't just go drilling holes into bus bars and landing terminals on there. You have to make sure that that is okay. Maybe there are existing locations to do this. Maybe there are ways to add splice points or use other types of connectors. Lots of different ways to make the supply side connection. If you're modifying the equipment, check with the manufacturer and make sure that's going to be okay. What about our labels? 70510 says, hey, we've got multiple sources of power, so we need to have a directory. Here we've got our PV system disconnect shown on the outside of the building. There's our AC combiner panel, so this would be our fused disconnect that we just sized. There's our AC combiner panel. Probably not a main breaker in there since we have the fuses here. This has our 5 backfed breakers, 80 amp breakers from the 5 inverters mounted along the wall here. And then inside, we're making the actual point of interconnection to that main service equipment inside the building. We've also have to mark our interactive system point of interconnection in accordance with 690.54. That's at our PV system disconnect or the point of interconnection. Probably put it on, you could put it on both. It doesn't really hurt anything. It's got our rated AC output current. So that's our 60 amps times 5 inverters and the nominal operating AC voltage, 480 volts in this case. Finally, we want to make sure that we label any equipment that's containing overcurrent protections from other multiple power sources as such. So 705.12, dual power source, second source is a PV system. That would be in the main service equipment where we're actually making that interconnection, and possibly in the PV system disconnect as well because, well, there's fuses in there and they're connected to the grid on one side and to the PV system on the other. All right, here's a basic schematic of where we're at so far. Not everything shown here, but I mean grounding shown. Just kind of a simple wrap of where we've gotten thus far in our system layout. Starting from the left, we've got our strings. Remember, we're using 18 modules in series, 11 strings in parallel per inverter. So we didn't show all 11, 1 to 11. You get what's going on. There's 8 more of them here. There's inverter 1. There's inverter 5. In the middle, 2, 3, and 4, everything is done symmetrically laid out. Everything looks the same. Each one of these inverters, the output is connected to the 80 amp breaker in our combiner panel. There, the combined current goes to fuse disconnect and then on to our point of interconnection. So this would be our PV system disconnect mounted outside the building as shown on the previous slide. We do show a main breaker here, but you don't really need that. It's redundant. One or the other is going to be where that's located. And then our main service panel, we didn't connect on the load side, so we're interconnecting to those primary power source conductors somewhere between the meter and the main disconnect in that service panel. Okay, up next, we will dive into conductor sizing for the AC conductors of the system. Talk to you soon.